Now, let me start with the 2D geometric transformations. And so the way to kind of look at this is okay, by which we mean that right, we want to have one operation, right, that we can apply, right, on, let's say, image I1, okay, in order to get I2. Okay, what we are looking at is a single operation which we can apply on I1 to get I2. Okay, and that operation could involve something like that could be something like, for all the guys here that are sitting here, so each pixel moves by the same amount. For example, if I say that there is a translation of tx pixels and ty pixels between the two, it actually means that if I were to shift every one of these pixels in I1 by tx and ty, right, it will if I shift this guy by tx and ty, I'll be able to reach the same pixel in the other image. Now, I mean, I will not be going to say talking about when you can do this and so on. Okay, there is already a certain set of, see, what happens is, right, there is a constraint on when it will happen. Okay, it's not always true that such a thing will happen. Okay, again, we will not go into when it can happen. It depends a lot on the even if it's a planar scene, right, there is something to do with the normal of the scene. Okay, that actually has a role to play. Then the other things that have a role to play is how did your camera move. Okay, did it purely translate or did it do something else? Okay, so all of this is a function of, so right, even though the way we will see it is, well, I can express one in terms of the other, but then when you can express it and all, right, is not something that I would answer, okay, in this course that I typically do when I teach, right, this in image processing. So there I sort of go into this details of when you get that and so on. Okay, so in this right, if I do that, then it will take a long time, so we will skip that. So we will start with what is called translation, right, which is the simplest of things. So, yeah, because, right, what can happen is, and again, right, if you have a rotation, for example, then what it means is, if you are actually if you are doing a rotation, right, about some point, then that point remains exactly at the same place in the second location. It doesn't even move. Whereas something which is actually close to that will move less, something that is farther off from the center will move more, and so on, right. So this kind of a pixel motion, okay, that happens, okay, right, between the images, it need not be a constant, right. That's what I'm saying. So when it is a translation, it's a constant, but then it doesn't always mean that, right, every time when you do this, there's going to be a constant motion or something. You can have each pixel moving, right, according to a certain law, right, depending upon what you're applying. But then the final notion is that there is one law, right, but there is one uniform law that you can apply, and that uniform law can cause a constant motion. It can cause a motion that varies across the image, but then there is still one law. Okay, whereas if you have a 3D scene, there is no single law. Okay, if it's a planar scene, okay, yeah, let me write that. So we are looking at a planar scene. Okay, so a planar scene, it need not be fronto-parallel or anything. By a planar scene, I mean it can be oriented at any angle. See, for example, right, I have a camera. When you say fronto-parallel, right, what it means is you need a plane exactly like that. Okay, that's a fronto-parallel plane. But then the scene itself, it could be like this, it could be like that, it could be anything. As long as it's planar, okay, if I could have taken an image from here of this scene, and then if I go there and take, right, one more scene wherever I am, right. Typically, if you have a complete 6D motion, then it means that I can go from here to anywhere I want, right. I just have to do an R and T, okay, right, in my 3D world. So if I go there and then right, I take a second image, I can always actually relate them. I can always relate them without even knowing, right, anything about the camera. Okay, right. That's the interesting part of this 2D geometric transformation. If you go deeper, right, then you will start to ask, right, things like what was the camera matrix, and then what was the actual motion that the camera underwent, what is the normal of the plane of the scene, right. That and all you can ask, but not in this course, right. But here we will just be interested in knowing, can I actually relate the two, and what does it take to actually relate the two, so that if I apply the transformation on the first image, I get the second, or if I do the inverse or whatever, then if I apply it on the second, then I can see the first, right. That's all we are interested in. So translation, right. So we will say that if I want actually a target and all of this, right, is at the this one, the spatial grid. Okay, all these operations are actually happening on the grid, on your spatial 2D grid. right. So it's like a purely geometric operation. Right? There's no photometric operation going on here. We are not increasing intensities. We are not right decreasing intensities. We are not doing anything. Right? We are just having the same scene, and we are trying to see how will this scene look like. Right? If I were to look at it from here, look at it from there. Strictly speaking, the physics of the scene should all come into play, but then all that we are ignoring. Right? Okay, so this is the simplest form, but the simplest form itself is enough for a lot of situations. So what we see is if I want a target coordinate, right? So for example, this is the spatial coordinates in my say target image, the spatial coordinates in my say target image. Target, if you are actually synthesizing, or you can think about x t y t as your I2, and then right, right, x and y1 can be your I1. And therefore, what you can think about is you can just write this as xs, ys plus translation tx, ty. Okay, and such a translation is called a global translation. Okay, and again, it's not true that it will happen every time. Under certain situations, it will happen. Okay, I am not here to talk about when it will happen and so on. Okay, so if such a thing is valid, okay, and if such a law holds, then we can actually relate these two images by simply knowing tx and ty. And of course, how do you know tx and ty? Because tx and ty will then have to be found out by your, if you go back to your feature correspondences, you can find out your tx and ty. Okay, a most general situation I will talk about, and these are all special cases of that. Okay, now this let's see if you have a situation like this, right, then what does it, so what things remain intact, right, when you do. So for example, it simply means that I have an image like this, and then right, if you do a translation, right, well, ideally the size and everything should remain the same. So it moves there, right. That's what we mean by a simple translation. So so in this case, right, what happens is angles and lengths are actually right, they actually remain intact, are preserved, okay, or they remain intact. Okay, everything is on the image plane. Okay, everything whatever I say is on the image plane.
So could you please explain the situation? Like first I am using a camera to take a particular image. And then on the camera plane I am moving the camera and taking a image.
Yes, yeah. So for example, if you had your image plane like this, right? Okay, all right. So it's like this, right? So okay, yeah. One more thing that maybe I should tell is, see, there is something called a pinhole model for a camera, right? A pinhole model, which is what we are following here. What this actually means is the following. Okay, what this actually means is that if you have a 3D scene, right, and then if you have a pinhole through which the light rays, right, from let's say each 3D point is entering, then behind this is actually was what is called an image plane. Okay, and from here to here, right, you may have a distance, whatever f or something, and then from here to here, right, this could be your depth d of that point. So what this means is that this point comes and actually hits the image plane here, and actually instead of seeing an inverted image, right, what we do is we actually think of the image plane as being in the front by a distance f. Okay, and what we mean is if I can get an image like this, okay, let's say so it's like saying that if I keep my camera here and I actually see this image, then if I see the scene, then I get an image. And suppose I translate this point now, right? That's my camera center. If I translate it on my, so it should be a parallel to this image plane. Okay, so my motion should not go forward or backward. Okay, so for example, right, if you have this as your image plane, then if I translate on the image plane and I take one more image, and under some condition, right, these two can be related by a simple tx ty. Okay, not always, like I said, it's not always true that if you do this, right, you will be able to see a constant motion of tx and ty, but there are situations when it can happen. Okay, so the image form, actually the same will also work if you had a lens under certain assumptions. Okay, whatever we say is actually for this one a pinhole, but if you had a focused image, see, the moment you get a blurred image and all, right, then the math changes a little bit. But then otherwise, right, if you think of a lens, even if you had a lens, right, instead of this, right, if you had a lens here, right? Okay, if you had a lens there instead of a pinhole. See, I'm not kind of going into why you need a lens and all that. I think most of you know that a lens is to right. I mean, take more light. See, for example, if you have a pinhole, right, then even though this point emits so many rays, only one ray can actually enter through that. Right, but this model is actually a sort of a convenient model in order to analyze what happens when images are formed, and this is an age-old model and it works in almost every case. But in a real camera, right, you don't have actually a pinhole, because a pinhole will mean that you'll have to wait for a long time, right, because only one ray is coming, right, which means that even to gather light I have to wait that long. That is the reason why you have lenses, because a lens can take all of these rays into it and then it can focus it right back at the same point, if it is a focused image, right. So a lens can gather all of the light quickly and then focus the image for you. If you don't have a pinhole, and again you need a lens, because if you just expand the size of the hole, what will happen? You just make this hole bigger. What will you see? What kind of a distortion will happen? Blurred, exactly, right. So if you keep, so it's not true that I can gather more light. To gather more light, I'll just increase the size of the aperture, right? That doesn't work. Okay, then you will have a blurring artifact. So what you need is actually a lens. Okay, so a lens will then bring in, focus all the light and give it to you as a focused image. I mean, if the image is not focused, which can also happen, that then goes into a different realm. We will not kind of enter into that. Okay, that we do in an image processing course. You got to stay away from that. That's a lot more involved. How depth is related and all that will come into play. But here, right, since I said that, right, depth, okay, in this 2D geometric transformation, we don't even want to refer to depth. Simply say a planar scene. Okay, we don't even want to talk about depth. Is that okay? Does that answer your question, or it's still okay? So always, right, think of, and of course you cannot have the image plane physically in the front, right? No, I mean, of course you cannot have it physically. This is just a model. Actually, it's always at the back, right? So you have a pinhole, and then at the back should be an image plane. But then, because you will see an inverted image, just to make the math cleaner, right, we just assume that the image plane is in the front. But physically, you cannot keep the image plane in the front, because the whole point of actually getting the rays through a pinhole is lost. Okay, so this is only a model. This is only a convenience thing, right? So you think of the image as being in the front by f instead of being at the back because then you will see an inverted image. Okay. So just to handle the invertibility and all, just say it's in the front. Okay, now the point is this, right? Now, so where was I? So then, right, in such a case, what we mean is, angles means all these is the internal angles, right? These internal angles and all don't change, and similarly the lengths and all, right, don't change. Whatever length you have here, the same length you see after you have done the translation. Then you can have actually a rotation, and this and whatever we are saying is all actually supposed to be in plane, which means that if you are rotating, then you are rotating like in plane. Again, if you kind of think of the camera center, and if you are rotating, again, you are kind of staying within the image plane. Okay, you're not kind of rotating. What do you say? I mean, right? So for example, you're not kind of doing like this, right? You're not doing like this, right? You're only doing like this. Okay, you're staying in the image plane and actually rotating. And normally, right, the way we kind of think of the x, y, z axis is like this, right? The optical axis and the z axis, typically we align them. Okay, so for example, so if you're going to think of this image center, right? So the image center will be such that, right, I'll have my x and y here, and then my z will be along the optical axis. That's the easiest way to then, so when you talk about depth, right, if you simply look at the z value, that will kind of tell you the depth. You can have a different transformation, it doesn't matter. I mean, then you just have to do the appropriate R and T to again align it back. But to begin with, it's always easy to think of the z axis as being aligned with the optical axis. Okay, so the optical axis is this guy. Okay, this is the optical axis, by the way. Okay, which is through the center of the through this one, the pinhole, and then through the center of this image plane. That's the optical center. That's the optical axis. Okay, rotation, right, will simply, again, this is an in-plane rotation, right. So it's easy. What you can do is you can have xt, you can have yt, and then you can say that this is like cos theta, sin theta. Yeah, I mean, right, depending upon clockwise or whatever, anti-clockwise, minus sin theta, cos theta. Then again, right, you can have source xs, ys. Okay, this will be a rotation, right, where this theta, right, you can tell what this theta is. And then one more thing is a small aside is that, right, when you're doing this, you want an image finally, right. This is only kind of saying what will happen on the grid, right. It's only saying that if you want to go to, if you know xs and ys, then where will xt be, right, if I tell you what my c theta is. But in reality, right, what we actually do is right, we don't actually go like this. We don't take, for example, right, there is something called a source to target versus a target to source mapping. Okay, so the equation, right, which right, I wrote, target to source mapping. So the equation that I wrote, right, I mean, it looks like you pick up the source coordinate and then you see, right, where it goes. So it's like saying that if I had an image which is the source image, and then if I want actually a target image, okay, then according to that equation, it looks like I pick an xs ys here, which is on this grid, find out right, where it goes here. That's like, so I pick an xs ys here, okay, and then I see, right, and then I see where it goes to some xt yt. And therefore, right, you would say that once I reach here, right, I might be able to say assign whatever is this intensity, I can assign to this point. Correct, right? Which is what you would do, right? Because finally you need to see an image, right? You have to assign intensities now. But then the problem is doing something like this creates what is called a situation of holes. In the sense that, right, if you do this, right, there is no sort of a guarantee that you will actually walk through all of them, all these pixels. You may actually end up skipping some of them. I mean, I'm not going into the technical details of that, but if you want, you can just read it up. Source to target, right? There's no guarantee that, see, because the point is what? Every pixel here should be assigned an intensity, right? Every pixel in the target image should get an intensity. There is no guarantee. If you go from source to target, that you will actually visit every one of them. There's no guarantee. What is called? It's called a phenomenon of getting holes in your final target. Hole doesn't mean you have zero intensity. Hole simply means that you don't even visit that pixel, right? It got skipped. Okay, I would have talked about it, but then it's again digression and it takes a lot. Just read it up. Okay, anywhere, source to target, why you don't do. So what we normally do is what is called actually target to source. What that means is, because I want to fill in IT, so I can always pick. I always go like on this integer grid. And again, right, see, remember that this tx, ty, everything can all be fractional. It doesn't mean that you have to move by only 1 pixel or minus 1 pixel. You can do like minus 2.75. It can happen, no? When you move a camera, there's no guarantee that you will get integer translations and all, right? So you need to be able to account for fractional shifts and all of that, right? So all that this target to source mapping, right, will actually take care of. So all that you do is, so for example, if you have an n cross n image, so your first pixel is 0, 0, and then you're going all the way till the end, which is like n minus 1, n minus 1. Then you start with every pixel here. You start with some pixel in xt, yt. So for example, right, so for example, if I had xt, yt, if you take the case of a simple translation, let's say I had xs, ys, what was it? So and then I had plus some tx, ty, right? And suppose I knew by some means that tx was, let's say, right, 1.25, and then ty was, let's say, whatever, right, 1.75, something like that, right? If I had, then what it will mean is I will actually subtract this from xt and yt, right? I will kind of take it to the other end. We will see later, right? I mean, how this entire option can be operation in terms of a matrix vector notation. If you do it, it becomes a matrix inverse. You'll see that later. For the time being, just assume that, right, this is the simplest, this is an algebraic thing, right, which you can do. And then now what you do is, now you actually fix an xt, yt, right? Now you take, let's say, xt, yt is 0, 0. Then you see, right, what do you get? I mean, after you do 0 minus tx and 0 minus ty, what do you get for xs and ys? Okay, so for example, right, normally, okay, what will happen is if you kind of fix a coordinate here for which you want to assign an intensity, correct? Every pixel in target image you want to assign an intensity. So when you sit on a pixel which is now an integer value, right, there is no fractional here, because in a target we know clearly that we are going from 0, 0, 0, 1, right? That's how we traverse. So when I'm sitting at an integer pixel, but then when I come back, right, using this kind of an inverse transformation, I come and land here in my source, but then I could land anywhere. There's no guarantee I'll land on an integer pixel. So wherever I land, but then, irrespective of where I land, there will always be four neighbors that I have, right, within let's say 1 pixel square, right? I'll land, if at all, if I'm lucky, I will land here or here or here or here. If not, I land somewhere inside a box, right, which is like 1 pixel width, always, right, wherever I am. Okay, right, wherever you are, you will always end up within a box of 1 pixel width. So then, Now the point is, okay, I have landed here, right, somewhere here. Now one thing is, one simplest thing which you can do is what is called, a nearest neighbor. Okay, so for example, so for example, if you feel that you are kind of closest to this guy, so whatever is this intensity which you know in the source, right, this intensity you know, no, so you can simply assign it to this guy here, or for example, if you happen to be closest to that gets intensity, but normally, right, that's not what is done. You do what is called a simple bilinear interpolation. So what that means is, if you are kind of say delta 1 from this guy and say delta 2 from this guy, and let us say this is your xs ys, and let us say, right, this coordinate is x comma y. What is x comma y in terms of xs ys? No. Let's have it in a more simple form. X is floor of xs and y is floor of ys, right? Just as you have seal, round and floor, right? So floor will so if it is 125.9, it will become 125. 125.1 will become 125. Whatever it is, it will become 125, right? So now this intensity, right? So now the intensity, okay, at xs comma ys. Now the coordinate we know. We want to say assign sorry, not at xs comma ys, at xt yt, right? That we want will then be, so then we can write this as 1 minus delta 1 into 1 minus delta 2 I of I source, right? Is, okay, what did I write? Is, right? Is at xy, not xs ys, right? This one. This coordinate is xy, this floor of xs and ys. I can't write xs ys, right? Xs ys is sitting here, that I do not know what it is. Oh, no, sorry, I wrote is. Correct. Yeah, is of x comma y, right? Is of x comma y plus, then I can write 1 minus delta 1, then delta 2 is of x plus 1 comma y. Then I can write, delta, what is it, delta 1 into 1 minus delta 2 is of maybe x comma y plus 1, and then plus delta 1 delta 2 of is of x plus 1 y plus 1. Okay, this is a simple, this is the simplest thing that you can do. This is simply a bilinear interpolation. This is called a bilinear interpolation, right? So it means that, so if you see delta 1 and delta 2 is 0, then ideally you should be assigning is of x comma y, right? Which is what will happen, right? Delta 1, delta 2, all the other terms will drop off, right?
In a way, I'm taking some kind of a linear combination.
Linear combination, yeah, that's all. You're just doing a weighted linear combination. Instead of 1D grid, if you would have 1D line, you would have taken between two neighbors. Now it's on a kind of 2D grid, so it will take 4 neighbors. You can increase the number of neighbors, by the way. If you go for a cubic interpolation, or if you go for a cubic spline and all, right, then you can take more and more neighbors. But then it's all about how much you gain by doing that versus right, doing something as simple as this. In fact, most of the cameras and all do, right, they do more sophisticated interpolation, because they have to anyway give you a picture that looks better than, and of course they have ways to implement it very fast and so on. But yeah, this is simply to tell you that even a nearest neighbor also you can do, but then that's not the most ideal thing to do. A simple thing that you can do is bilinear interpolation, and that's how you will get the image. Finally, right, you want to be able to get the other image, right? If you are synthesizing, this is if you are doing some kind of a data augmentation or something, right, where you want to synthesize the other image given the first. Okay, then scaling is another thing which you can think of, right, which is a simple. Okay, now in rotation, right, I still haven't written the properties, right. I have to write in terms of so angles and lengths. Again the same thing as this. Okay, ditto. What he said, ditto. So it's like this, right? You have an image like this, then right, it becomes like that. All the internal angles stay intact. If this is a right angle, this remains a right angle. Legs stay the same, and this is called actually a Euclidean motion. Okay. Then you go to the next level, which involves scaling. So when you get into scaling, right, then you have something like what is called uniform scaling. Okay, you can also have non-uniform scaling, but we'll just look at uniform scaling. So it will be like S0, 0S, and then XS, YS. All of that will still apply. Okay, whatever I said, this is a target to source, and all of that will apply. So for example, right, suppose I said that, right, you wanted to do a soft zoom, right, in your lab assignment. Suppose you had to zoom in an image. What will you choose here as your S? Should S be greater than 1 or should S be less than 1 if you wanted to zoom? Zoom, yeah, let's see, right. So what do you get? So xt is S times xs, S times xs, and yt is S times ys, right? Yeah. So if you wanted to zoom in, S, yeah. So then zoom in. So what this means is this, right? So you have your IS already with you, and then you have a target here, right? And you see what you are saying is, if this portion, right, goes and sits as a smaller thing inside, that will be what? That will be zoom out, correct? Because this, so it's like going back. But then when you go back in a real camera, you don't get zeros, right? You get something else, right? Whatever else is in the scene, that will enter. But then in a simulation, you don't. I mean, unless of course you have a boundary that you can extend and you know what lies outside, then you can fill it up. But normally, right, if you zoom out, it will mean that you have zoomed out. But so whatever is this portion that's appearing in a smaller area, right, in IT. Whereas if you zoom in, right, it'll mean that right, a portion of this will occupy all of your target, right. That'll be zoom in. So in one case your S is going to be greater than 1, the other case S will be less than 1. So you can actually create these effects, right. Again, all this will involve that bilinear interpolation, and then you can create a zoom in, a zoom out, whatever you want. Okay. Then okay, now with scaling, right, what will happen is, so with this uniform scaling, so when you scale, right, angles are actually preserved, but not the lengths, right. But the ratios of lengths are preserved. Okay, ratios of lengths are preserved. And the combination of this is what is called a similarity, in the sense that, right, you can have xt, yt, right, you can have scaling, you can have a rotation, okay, or else I will just simply, instead of repeating all this, I will simply write this as S into R, and then you have xs ys plus a tx ty. Now the way I am still writing it is somewhat kind of say clumsy. Okay, there is a much more neater way to do this, but I didn't want to say bring that now at this stage. I thought we'll do it right in the next class. So right now, right, think about a uniform scaling, a rotation, and a translation. So how many unknowns are involved? How many unknowns are involved in this? So scaling, there is one unknown. For rotation, there is one theta. Then translation, tx and ty, four unknowns, right? So this is called a similarity transform, called a similarity transform, or a similarity, right? That's what it's called. And the similarity, right, again. So for this, and all those are actually, so the earlier ones are kind of a special case. If S is identity and T is 0, then you get rotation and so on. So angles are actually preserved, and so it's like saying that you have this, right, and then you kind of rotate, and then it should be something like that, right? You scaled, rotated, translated. Angles are preserved, and what is this? So and ratios of not necessarily parallel. Okay. Lengths. That also applies to this, by the way. Lengths are preserved.
This matrix should act on translated and rotated image, or only on the rotated?
No, so the point is how you choose your S and R, right? So it's like what is your eventual goal? Okay, so how you choose your S, R, and Tx and Ty, right? I mean, it's like saying that in 1D, right, when you do x of at plus b, okay, that you can do either by, say, translating first, and then you apply the scaling. If you scale first, right, then it should actually translate. You should scale the translation, right? So what A and B, right? There, what you need, right? So what you need, you have to fix, right? How you want it. Similarly here, right? Depending upon what you, for example, right, I can also have a situation where I want to translate first and then apply an R, which will mean that my actual transformation will then become R into x minus Tx, y minus Ty. That's also possible. Okay, but then if you want to write it in terms of a tx and ty, then the tx will become cos theta times this tx and so on, right. So it's just a matter of how you write it. Just an unknown. So you have to fix it. You have to know by what you want to do. See, normally what happens, if you want to synthesize, you should know what you want to do, in which case you tell what should be the theta, and the order you tell. I'm going to rotate first and then translate, right. I mean r xy plus whatever plus is tx dy. If you want to do it the other way, then again you should choose your tx and ty, because they will then change, because then you will be pushing tx ty into xs and ys. Okay, so we will stop here.